This video is for class 9th science physics part chapter 10 gravitation. In the beginning part of the video I have discussed the complete theory of the chapter in form of handwritten notes, and towards the end I have discussed the textbook questions followed by answers. So first, what this chapter has. So the beginning part of the chapter talks about gravitation and something related to centripetal force, centrifugal force. Then comes the universal law of gravitation. Then a small note about Isaac Newton, who has given the universal law of gravitation, and then how Newton guessed the inverse square law, followed by the here itself there is Kepler's laws of planetary motion. And then there are some numerical problems where we will understand how to calculate the force of gravity between any two masses separated by some distance. And then there is importance of universal law of gravitation, and then the meaning of free fall, and then common relation between acceleration due to gravity and gravitational constant. A derivation is there. Then calculation of acceleration due to gravity of Earth as well as Moon, followed by the equations of motion when objects are in vertical motion, and a few examples where we apply the three equations of motion when acceleration due to gravity A is written as a g. Then concept of mass and weight, we will differentiate these, and then we will calculate what happens to weight of an object on Moon, followed by the concept of thrust and pressure. Here we come into the fluid dynamics concept. So pressure in fluids concept, and then buoyancy, why an object floats or sinks in a particular medium. So here they talk about water. So once we understand why an object sinks and floats in water, we can relate this to why an object is going to sink, or whether an object is going to sink or float in a particular fluid. Then Archimedes principle, and with Archimedes principle the topic gets over. Then we have density, relative density, and then we come to textbook exercise questions. There are few of them which we will answer. So this is how we are going to learn this chapter. To understand this chapter, I have prepared some handwritten notes. Like I read the complete chapter, concised the information, and I have prepared this handwritten notes. So in the handwritten notes, I have written, first jotted down what topics are there in this chapter. So chapter 10, gravitation. In this chapter we will learn about gravitation, universal law of gravitation, motion of bodies under gravitation, how weight of a body varies from place to place. That means weight of a body depends upon which factor, and that factor how it varies from place to place on Earth, and the conditions for an object to float in a fluid. So these are topics we will learn, and I have prepared the handwritten notes. That means why this handwritten notes? Because before any exam you can just sit back and watch this complete video, and you are well prepared for this exam, for that exam where gravitation chapter is involved. Now starting with the first topic of gravitation chapter, it is about universal law of gravitation. But before that I wrote a point. This point is, what is the meaning of gravitation? Gravitation is an attractive force. You must be knowing different types of forces which may be attractive in nature or repulsive in nature. For example, magnetic force or electrostatic force. They are attractive as well as repulsive in nature. But gravitation force is the only force which is attractive in nature, and it is the weakest of all forces. So gravitation is the attractive force and it is the weakest. As we proceed in the chapter, we will know why gravitational force is the weakest force. Then the chapter begins with the universal law of gravitation that you saw in the textbook. So here I added two more points. Universal law of gravitation is otherwise known as Newton's law of gravitation. Why? Because universal law of gravitation was proposed by Newton. So it is otherwise known as Newton's law of gravitation. In Newton's law of gravitation, we will see one phenomena. That phenomena is force and distance of separation between the masses is an inverse square relation. That is why Newton's law of gravitation is otherwise known as the inverse square law. Why did I write 3 different names of the same law? Because sometimes in the examination, the examiner doesn't ask the question directly saying that state universal law of gravitation or by application of universal law of gravitation. It is not necessary. Sometimes they say state the inverse square law. So inverse square law is universal law of gravitation. This inverse square law also comes in the Coulomb's law also. But since this chapter specific, that is why inverse square law is also otherwise the Newton's law of gravitation. So remember the 3 different names of the same law. So what is the definition of universal law of gravitation, Newton's law of gravitation or inverse square law? It states that every object in this universe attracts the other object with a force which is directly proportional to the product of their masses and inversely proportional to the square of distance of separation between the masses. So this is such a rhyming statement. We are supposed to kind of remember it. So what is Newton's law of gravitation? Newton's law of gravitation or universal law of gravitation or inverse square law states that the force of gravity between any 2 masses, if they are separated by some distance r, that force of gravity is directly proportional to the product of the magnitude of the masses and inversely proportional to the square of the distance of separation between those masses. That's a statement. This statement I have written in mathematical form. So first a diagrammatic understanding. So these are any 2 masses of magnitude m1 and m2 separated by r distance. Keep this in mind. Distance of separation between the masses, meaning is distance between the centers of the 2 masses. So r is a distance between the centers and m1 and m2 are the magnitude of the masses of these objects. Mass means quantity of matter possessed by an object. So how much force of attraction means force of gravity is there between them as per universal law of gravitation. Force of gravitation between the masses is directly proportional to, this symbol is the direct proportionality symbol, directly proportional to the product of the masses means magnitude of masses and inversely proportional to the square of the distance between the masses. This is the mathematical expression of the statement that I just read out. When we club these two, clubbing meaning is force is force, but these two we have to multiply. So m1 into m2 times 1 by r square is m1 into m2 by r square. And whenever we remove the proportionality symbol, we have to put is equal to and a constant of proportionality. Here in this case, the constant of proportionality is denoted with capital letter G. So ultimately we get the mathematical formula for universal law of gravitation or Newton's law of gravitation or the inverse square law. Mathematical expression is F is equal to G m1 into m2 by r square. So G is the constant of proportionality, otherwise known as the universal gravitational constant. So force of gravity can be calculated using the product of universal gravitational constant times the masses of the 2 objects divided by the square of the distance of separation between the masses. So this is universal law of gravitation. So we came across a new physical quantity, that is universal gravitational constant. Universal gravitational constant is otherwise in short called as gravitational constant. First of all, why is it called universal gravitational constant? It is called universal gravitational constant because this is a constant that remains a constant everywhere in this universe. That's why it is called universal constant, and it is related to gravity, so it is universal gravitational constant. With as we proceed in the chapter, instead of using the word universal, we will cut short and say gravitational constant. Gravitational constant is always denoted by the letter capital letter G only, not small letter. Be careful on this. So this we found in the mathematical expression of universal law of gravitation. that is F is equal to G m1 into m2 by r square. So here we make slight changes, like r square we multiply to this and m1 m2 we bring down. So by making minor changes, by transposing r square m1 m2 the other side, we will get the mathematical expression for universal gravitational constant, which is G, which is F into r square by m1 into m2. But you are not supposed to by heart this one. You only remember Newton's law of gravitation, that is F is equal to G m1 m2 by r square, and whenever we want the value of G, we can figure out what is G value in terms of F r square and m1 m2. So G is equal to F r square by m1 into m2. Now what is the SI unit of this physical quantity? SI unit we will calculate from this. F is measured in terms of Newton, R is meters, masses in terms of kilograms. So SI unit of gravitational constant is Newton meter square per kilogram into kilogram, means kilogram square. Newton meter square per kilogram square. Now let us define the universal gravitational constant. How to define? For defining, we have to do minor changes in this formula. We want to know the definition of G. So if we take some unit masses, that means the masses are 1 gram or 1 kilogram or 1 unit of mass separated by 1 unit of distance. Unit means 1. When this becomes 1, then universal gravitational constant becomes equal to the force of gravity between the unit masses separated by unit distance. In that way, universal gravitational constant is defined. So the definition is like this. Universal gravitational constant is the force of gravity between any two unit masses separated by unit distance. Means when the masses are unit of 1 of any unit of mass, r is also 1 any unit of distance, then these all become 1, then G directly becomes equal to F. So universal gravitational constant becomes equal to the force of gravity between any two unit masses separated by unit distance. Value of universal gravitational constant was first found by Henry Cavendish. Henry Cavendish lifespan is written, that he did by a particular experiment, but that experiment is not in our syllabus, but that's an interesting experiment to know how the value of G was found. But what is the value of G? Let us find it. The value of universal gravitational constant is 6.67 into 10 to the power minus 11 Newton meter square per kilogram square. This is something we have to remember about gravitational constant. Now moving ahead, about universal gravitational constant. Universal gravitational constant is independent of masses of the bodies and distance of separation between the masses. Nature of the medium, shape and size of the bodies, means it is a constant. It doesn't depend upon almost anything. Value of G is extremely small. Just now I told that G value is 6.67 into 10 to the power minus 11 Newton meter square per kilogram square. So G is some number which is in 10 to the power minus 11. 10 to the power minus 11 is such a negligible number that the value of G, since it is extremely small, so force of gravity between two objects is automatically very much weak. Like what is the meaning of this sentence? Force of gravity between any two masses is calculated using the formula G m1 into m2 by r square. Now the masses, the two masses be whatever, huge, small, whatever. Distance between those masses may be less, may be more, unnecessary. But this complete thing is multiplied to a very small number, means 10 to the power minus 11, a negligible number. So however big the masses be, since it is multiplied to a negligible number, then overall the number is a negligible number. So force of gravity ultimately between any two masses separated by some distance is a negligible number. That is why force of gravity is mild or weakest force. Now coming to the importance of universal law of gravity, where force of gravity is used. Force of gravity is due to which the satellites revolve around a celestial object, or the planets revolve around sun, the Milky Way galaxy's movements, those all. So because we have to write something in the exam, so I have just jotted down some points so that easily we can note down these points. Importance of universal law of gravity. Gravity is that holds the terrestrial objects on earth. Terrestrial objects means every object on earth is held, including the atmosphere, means air, is intact with earth due to gravity. Gravity can hold every object, and air also has some mass, so that gravity holds the terrestrial objects on earth. Gravity holds atmosphere, causes rainfall. Rain falls, rain doesn't fly, so rain falls due to gravity. Snowfall on earth. Moon revolves around earth, planets revolve around sun, satellites revolve around the planet, all of them due to gravity. Now that we have learnt the mathematical formula for force of gravity between any two masses separated by some distance, as F is equal to G m1 into m2 by r square, let us see how to apply that formula to calculate force of gravity between some typical kind of masses or special cases kind. So the first case, how to calculate the force of gravity between any two masses which are 1 kilogram each separated by 1 meter distance, means what is the force of gravity between unit masses separated by unit distance. Unit means 1. Force of gravity is F is equal to G m1 m2 by r square formula. In place of G, 6.67 into 10 to the power minus 11. Masses are 1 kilogram each, so I have written one of them, 1 into 1. R is 1 square. So these 1, okay, fine. So how much is force of gravity? Force of gravity is 6.67 in 10 to the power minus 11. And since it is force, it is measured in terms of newtons. So force of gravity between any two unit masses separated by unit distance is 6.67 into 10 to the power minus 11 Newton. Though this much of calculation is done, but it is a kind of thing that should be remembered. Like, what is the force of gravity between unit masses separated by unit distance? It is equal to 6.67 into 10 to the power minus 11 Newton. The second case, where we have to calculate the force of gravity between an object of mass 1 kilogram and Earth whose mass is 6 into 10 to the power 24 kilograms. Radius of Earth is 6400 kilometers. So in this chapter, there are good number of constants that are there which we have to remember. First constant is the value of universal gravitational constant, that is 6.67 into 10 to the power minus 11. Next is mass of Earth, that is 6 into 10 to the power 24 kilograms, and radius of Earth, which is 6400 kilometers. This is easy to remember. Later, most of the time we have to convert that to meters. So radius of Earth is 6400 kilometers, which is 6.4 in 10 to the power 6 meters. So what is the force of gravity between any object of mass 1 kilogram and Earth? So we are using the force of gravity formula. F is equal to G m1 into m2 by r square. G is a 6.67 into 10 to the power minus 11. Mass 1 kilogram. Mass of Earth 6 into 10 to the power 24. Distance of separation between that 1 kilogram object and Earth. Every object on Earth is within the radius of Earth, because there are huge mountains and valleys. So all of them comes within the radius of Earth. So 6400 kilometers, which is radius of Earth, is an approximate number. So a distance between 1 kilogram object on Earth and center of Earth, that distance is this. So in place of R, in terms of meters, SI unit 6.4 into 10 to the power 6, R square, so square. How to solve this kind of numbers? For solving, first assemble all the numbers together, then assemble all the 10 to the powers, means assemble the numbers without decimals, means this number can be written as 667 into 6 divided by 64 into 64 because square is there. And then assembly of 10 to the power. So here decimal, if it is removed, this gives 667 into 10 to the power minus 2. Here 10 to the power minus 11. Here 10 to the power 24. This contributes 2 zeros to the numerator. 10 to the power 6 into 2 means 10 to the power 12. When it comes to the numerator, becomes 10 to the power minus 12. So I assemble all the numbers. 6.67 into 6 by 6.4 into 6.4 into 10 to the power all assembly, and here decimal after 2 digit, and here also decimal after 1 and 2. So here you can forget decimal. This set of numbers, when it is calculated along with this is 24 minus 23 means a 10. This is 10. So this definitely is 0.98. 0.98 into 10 is 9.8. So force of gravity between a 1 kilogram object and earth is 9.8 Newton. This is the second number that we have to remember in this chapter, which is shown here in form of calculation. The first one is, what is the force of gravity between any two unit masses separated by unit distance? That is 6.67 into 10 to the power minus 11 Newton. This is that G value. Then what is the force of gravity between 1 kilogram object and earth? It is 9.8 Newton. 9.8 is what it, as we proceed in the chapter, we will know that 9.8 is the acceleration produced in every freely falling body on the surface of earth. So 9.8 Newton. The third one, what is the force of gravity between earth and moon? Mass of earth, as I said, we have to remember 6 into 10 to the power 24 kilograms. Mass of moon is 7.4 into 10 to the power 22. It is easy to remember in terms of 10 to the powers. Earth is, mass of earth is 100 times mass of moon, because mass of moon 10 to the power 22. Mass of earth 10 to the power 24. So approximately mass of earth is 100 mass of moon is equal to mass of earth. The distance of separation between earth and moon is 3.84 into 10 to the power 8 meters. We are using F is equal to G m1 m2 by r square to calculate force of gravity between earth and moon. So in place of G, 6.67 into 10 to the power minus 11 Newton meter square per kilogram square. Mass of earth 6 into 10 to the power 24 kilograms. Mass of moon 7.4 into 10 to the power 22 kilograms. Radius means a distance between center of earth to center of moon, 3.84 into 10 to the power 8. Here square, so here square. So this, how to solve? Assemble all numbers together, means 667 into 6 into 74 by 384 by 384 times 384, and then assemble all 10 to the powers, means 10 to the power minus 2 minus 11 plus 24 minus 1 plus 22 plus 4 minus 16, and then all the numbers when we solve, we will get force of gravity between earth and moon is a 2.01 into 10 to the power 20 newtons, which is big, quite big, because 10 to the power 20 newtons, double this number. So force of gravity between earth and moon is 2.01 into 10 to the power 20 newton, worth remembering. Now coming to Kepler's laws of planetary motion. Before I discuss Kepler's law of planetary motion, I would like to tell who are the giants or scientists, philosophers who have given information about planetary motion. The first one in the line was Copernicus, who first proposed the sun-centric theory. The meaning of sun-centric theory is sun is at the center of the celestial system, means the solar system in a way. So sun is at the center and earth and remaining planets revolve around the sun. So Copernicus gave the sun-centric theory. Prior to sun-centric theory, the popular theory was the geocentric theory that was proposed by Aristotle. Aristotle's geocentric theory's meaning is geo means earth is at the center of the solar system and sun and remaining planets revolve around earth, which was proved wrong through statement, of course. by Copernicus. Copernicus' sun-centric theory was further claimed true by Galileo, because Galileo was the first person who discovered the telescope, and through his observations through the telescope, Galileo said the sun-centric theory is true. After Galileo, it was Kepler who, through his laws of planetary motion, further proved the correctness of sun-centric theory. Means sun is at the center of the solar system, remaining planets and other celestial bodies revolve around the sun. And after Kepler, it was Isaac Newton who proved all the planetary motion, laws of planetary motion, and since he proved those all, so most of the laws of planetary motion or motion of bodies in the universe, those all credit goes into Isaac Newton's account. So Isaac Newton often says that I'm not great, I am appearing great because I am standing on the shoulders of giants. Very popular statement by Isaac Newton. Now coming to Kepler's laws of planetary motion. Kepler gave 3 laws of planetary motion. The first law is called law of orbits. Second law is called law of areas. Third law is called law of time periods. So Kepler's first law, which is called law of orbits, states that, I have written the statement but I am telling what it is. So Kepler's first law of planetary motion is called law of orbits. It states that every planet revolves around the sun in elliptical orbit, keeping sun at one of its foci. You understand that circle has one center, but ellipse will have 2 focuses. So planets revolve around the sun in elliptical orbits, keeping sun at one of its foci. Foci is a singular of the word focus. So that is law of orbits, means planets revolve around the sun in elliptical orbits. Kepler's second law is called the law of areas. First I will state it, then I will tell you what it means. Law of area states that the line joining the center of the sun to center of the planet sweeps out equal areas in equal intervals of time. That's a statement to be remembered, quite rhyming also. So second law, which is law of area, states that, you just see this, the planet in elliptical orbit with sun at one of its foci. Now from location A to location B, if the planet has taken some t1 time, and from location C to location D, if the planet has taken the same time t1, so A to B how much time, C to D if the planet takes the same time, then the line joining the center of the center of the sun to the center of the planet, the line joining the center of the sun to center of the planet sweeps out equal areas in equal intervals of time. That means time taken from A to B, if it is same as time taken from C to D, then area of sector AOB is same as area of sector COD. That you can guess also because focus is here. So this area is definitely equal to this area if we know the sector angle. Sector angle depends upon length of arc. Length of arc depends upon the time lapsed in traveling this zone and this zone. So what is law of areas? Law of areas states that if time taken, it states that the line joining center of the sun to center of the planet sweeps out equal areas in equal intervals of time. That means this area and this sector areas are same in equal intervals of time. That means if this time and this time is the same. That's the second law. Kepler's third law is related to, is called a law of time periods. It is related to the time taken by a planet to complete one revolution around the sun. So Kepler's third law, law of time periods, it states that the square of a time period of a revolution of a planet around the sun is directly proportional to the cube of the distance of separation between sun and the planet. So Kepler's law of time period, square of time periods of revolution of planet around the sun is directly proportional to the cube of the distance between the planet and the sun. So this you can understand by the information that Mercury completes very quickly one round around the sun, whereas Pluto takes some months to complete one round around the sun. That means the time period is a directly proportional to the distance between planet and sun. If planet is close to the sun, its a time period of revolution around it. That means its a 1 year is very small. And if the planet is very far from the sun, then its 1 year is quite a good amount of time. So that is the law of time periods. In the Newton's law of gravitational mathematical expression, we saw that force of gravity between any two masses separated by some distance is calculated using the formula F is equal to G m1 into m2 by r square. Means force of gravity is inversely proportional to the square of distance of separation between the masses. So this relation was told by Newton. In that case, how did Newton guess? How Newton guessed the inverse square law? Why universal law of gravitation is otherwise known as inverse square law? It is because force of gravity is inversely proportional to the square of distance of separation between the masses. This is called the inverse square law. And how Newton guessed this? For that, there is a small proof that we have to see. Since around the sun the planets revolve. So this is the planet. The distance between the planet and sun, that is r. Say for example, r is the distance between sun and planet, and m is mass of the planet. R is the distance between sun and planet, and m is mass of the planet. And v is the orbital velocity of the planet. That means velocity with which this planet is revolving around sun. That is called orbital velocity of the planet. So m is mass of the planet, v is orbital velocity of the planet, r is the distance between center of sun and center of the planet. In that case, when the planets revolve around the sun, it is under balanced forces. One is the inward force and another is the outward force. The inward outward forces are opposite in direction but equal in magnitude. The inward force is called centripetal force. The outward force is called centrifugal force. Now when planets are revolving around the sun, the inward force is called centripetal force. So between planet and sun there is centripetal force as well as force of gravity. Centripetal force between planet and sun is calculated using the formula mv square by r. M is mass of the planet, v is velocity of the planet in its orbit, r is a distance between sun and the planet. So this formula is the formula for centripetal force. You can remember this. Then orbital velocity. So what is the velocity of the planet in its orbit? Velocity is what? A distance traveled by time taken. What is the distance traveled by the planet in its orbit? If for a while we assume that the orbit is not elliptical and it is circular, then distance traveled by the planet in its orbit is equal to circumference of the circle, means 2 pi r. So what is right? First, this is centripetal force. Here we have orbital velocity. How to calculate orbital velocity? It is the distance traveled by time taken, time period of revolution of the planet around the sun. So 2 pi r by t. Here we have v square. So square both the sides. Then we will get v square is 2 square, which is 4 pi square r square by t square. We get something like this as v square. And then this v square we will substitute in centripetal force formula. So we have F is equal to mv square by r, equation 1. V square as equation 2. We will substitute equation 2 in equation 1. When we substitute, we will get F is equal to mv square by r. But v square is 4 pi square r square by t square. Then from this stock, we will take all the constants out, like m 4 pi square. And this r and r square cancel, so we will have a single r in the numerator by t square. Up to this, fine. Then at this stage, to the numerator and denominator, we will multiply r square. When we multiply r square at this stage, then we will get r into, see, this all is constant. R into r square is r cube. Then we have t square, and this r square stays in the denominator. So m is mass of planet, which is a constant. 4 pi square is also a constant. Then r cube by t square. R cube by t square is also a constant by Kepler's third law. Kepler's third law is t square directly proportional to r cube. So, or you can write r cube proportional to t square, or r cube by t square is a constant. So here these all are constants, and 1 by r square stays outside. We know that whenever we want to replace proportionality symbol, we put is equal to and constant. This time this is equal to and constant we will replace with the proportionality symbol. So we get F is equal to constant times 1 by r square, or F proportional 1 by r square. So force is inversely proportional to square of distance between the masses. And this is how Newton guessed inverse square law. So carefully observe the steps that I discussed. Sometimes pause the video, or sometimes take the video a bit back to see what are the stages in the derivation for how Newton guessed inverse square law. First, centripetal force mv square by r. Then orbital velocity 2 pi r by t. We want v square, so square throughout. And then in this formula v square, we have to substitute. After substituting, put all the constants aside, then we will get r by t square. At one stage, multiply r square to the numerator and denominator, and then you get r square into r, which is r cube by t square. So these all are constant. Only 1 by r square stays outside. So F is equal to constant times 1 by r square. Is equal to constant is actually proportionality. So F proportional 1 by r square. And this is the inverse square law. We have already seen the application of Newton's law of gravitation, F is equal to g m1 m2 by r square. These calculations, like in form of numbers, like what is the force of gravity between any two unit masses separated by unit distance, that we have seen. But in this part of the video, I want to show how the calculation is done. So for the first one, force of gravity between unit masses separated by unit distance. Remember this statement. So how to calculate? Force is g m1 m2 by r square. G is 6.67 in 10 to the power minus 11 Newton meter square per kilogram square. Mass is m1 m2 1 kilogram each by 1 meter square. So here this part I am showing you so that you understand how the calculation is being done. So here kilogram square gets cancelled with this kilogram into kilogram, and meter square cancels with this meter square. So ultimately we are left with Newton, which is the unit of force. Now when we multiply all this, we will get 6.67 into 10 to the power minus 11 Newton. Next, force on 1 kilogram object held on the surface of earth. That means what will be the force with which a 1 kilogram object is pulled towards the center of the planet. So this calculation also I have shown in the previous part, but I want to show you how the things are calculated. So we will use the formula F is equal to g m1 into m2 by r square. G is 6.67 in 10 to the power minus 11. One of the mass is 1 kilogram. Another is mass of earth. R is a radius of earth square. How to solve? To solve, we have to place all the numbers together without decimals. So 6.67 is 667 into 6, denominator 64 into 64 square. So I collected all the numbers together in one stock and then have a collection of 10 to the powers. 6.67, so this contributes -2, -11, 10 to the power 24, this one. Denominator 0.1 square means that contributes 2 zeros to the numerator, so +2. 6 to 12 in the denominator, that is -12. 6 to 12 plus 12 in the denominator is -12 in the numerator. So all the 10 to the powers are collected. Then 667 into 6 is a 4002. You can remember this because force of gravity between 1 kilogram mass and earth, whenever we calculate, numerator is going to be 4002, denominator is 64 square, which is 4096. And here sum of positives, from that sum of positives is 24 plus 2, 26. From that we have to subtract the sum of negatives, 2 plus 11 plus 12, all of them negative, that's why -25. 26 minus 25 is 10. 4002 by 4096. Literally you are not supposed to divide these all because radius of earth, mass of earth, all of them are approximate numbers. So in physics we can show the last answer as approximate answer. 4002 by 4096. Just concentrate on the first two digits, 40 by 40. So it should be 40 by 40 should be 1. But here denominator number is greater, almost 100, greater than the numerator number. So overall fraction value, which based on 40 by 40, which should be 1, when these digits are included, because denominator is a bigger number, so overall fraction value will be a bit less than 1. That a bit less than can be 0.99, 0.98, 0.97, any of them. So when you divide them, you will get something like 0.99 or 98 or 97. I chose 98. And into 10 to the power 1. So this number, when we multiply to 10, decimal shifts one place, and then force of gravity between a 1 kilogram object and earth is 9.8 Newton. The next calculation of force of gravity is force of gravity between earth and moon. This also a number to be remembered. So force of gravity between earth and moon is 2.01 into 10 to the power 20 newtons. Gravity is stronger due to earth, so moon keeps on revolving around earth. For that we have to remember mass of earth, mass of moon, distance between earth and moon. These are nice numbers to remember. 6 into 10 to the power 24 kilograms, 7.4 into 10 to the power 22 kilograms, because 100 masses of moon is 1 mass of earth. 24, here 22. Radius, distance between earth and moon, 3.84 in 10 to the power 8 meters. Universal gravitation constant, however, we know we should calculate force. Which formula we are using? We are using F is equal to G m1 into m2 by distance between the centers of these two masses. So we placed all the values. Okay. Then what is the way of solving when coming to this? You have to collect all the numbers in the numerator denominator without decimals. Means here 667, 64, 74, 384, 384, and then collect the 10 to the powers. So 10 to the power, this contributes a -2, so 10 to the power -2. Then 10 to the power -11, this contributes 10 to the power -1, plus 10 to the power 24, 10 to the power -1, 10 to the power 22. This and this contribute 10 to the power 2 and 10 to the power 2 to the numerator, in fact. So 10 to the power 4 plus 10 to the power 8 into 10 to the power 8 is 8 plus 8 is 16 in the denominator. So that comes to the numerator as -16. So this is the collection of 10 to the power. So here we have to collect, or we have to add the positives, and from sum of positives we have to subtract the sum of negatives, which turns out to be 50 positives. Sum of positive numbers is 50. Sum of negative numbers is 31. Negative numbers, when they are added, the negative symbol stays. So 50 minus 31 is output from this zone. When we multiply the numerator numbers, this turns out to be this. Denominator numbers turns out to be this. Now, you see, here how many digits? 7. Here 6. So like 14, at least this will be enough. 14 into what is close to 300, or 147 into what is close to 3015. Very simple. 147, think that it is 150, and 3158, consider that this is as 3000. 150 by 3000 is a definitely 15 by 30 kind. 30 is a 2 times 15. So this number divided by this number is close to 2. 14745 into 2 is going to be this one. So in that way, when we divide this, the approximate number is this is 20 times, like not 2, because here the decimal, okay. So this into 20, because digits 7 and 6. So this into 20 is this. So 20.1 approximately. 50 minus 31 is 19. 50 minus 31 is 9, 10 to the power 19. Every time we get the answer like this, this cannot be considered as an answer. Why? Because it is not in standard form. For standard form, the decimal has to be shifted one place left. In that case, we will get 10 to the power minus 1. To understand that standard form, multiply and divide by 10. So that this 10 contributes to this. 19 plus 110 is 10 to the power 20. This denominator 10 means 20.1 by 10. Shift the decimal here. So force of gravity between Earth and Moon is approximately 2 times 10 to the power 20 newtons. Having learnt the applications of Newton's law of gravitation's mathematical expression, let us come to know the relation between gravitational force and Newton's third law. What do I mean? Gravitational force is the force with which any two objects having certain mass separated by some distance are attracted towards each other. Then, is it that when the two objects are of different masses, like an apple and earth, do apple also pull earth with the same force with which earth pulls the apple? Now let us answer or see this question. An apple falls towards earth due to earth's gravitational pull. But why we do not see earth rising towards the apple when Newton's third law is a universal law? Excellent question. That is why we see only apple falling towards earth and we don't see earth falling towards apple. We will see if we stand on apple. We are standing on earth, so we see apple coming towards us. We will see earth falling towards apple when we are residents of apple, not earth. Now let us see how to answer that question. Mass of apple is less than mass of earth. And by Newton's second law, acceleration produced in an object is directly proportional to force. And in this case, force of gravity is the same for apple as well as earth. Force with which apple is pulled towards center of earth is equal in magnitude and opposite in direction to the force with which earth is being pulled towards center of apple. And acceleration produced in the bodies is inversely proportional to mass. Here the point is, more mass, that object accelerates less. Less mass, more acceleration is produced. So apple's mass is less. So more acceleration is produced in apple. But mass of earth is more. So acceleration produced by in earth due to apple's gravitational force is comparatively less. Mass of apple is less, so acceleration produced in it is more due to earth's gravity. But mass of earth is comparatively huge, so acceleration produced in earth is less due to apple's gravity. That is the answer, that why we see apple falling towards earth and we don't see earth falling towards apple. Now coming to the topic of free fall. What is the meaning of free fall? Free fall word holds for every celestial body, not just for earth. So any body that falls towards the or away from the planet. So any body that is falls towards or goes away from a planet, it moves with an acceleration due to gravity of that planet. That acceleration is called free fall. For example, objects on Earth are accelerated with 9.8 meter per second square under free fall, and objects on Moon are accelerated with an acceleration of 1.63 meter per second square on Moon. Now coming to the topic of how to derive, like we are going to derive a common formula or relation between acceleration due to gravity, that is small letter g, and universal gravitational constant, that is capital letter G. So how these two are connected? Universal gravitational constant is a constant, literally depends upon nothing. It's a value 6.67 into 10 to the power minus 11 Newton meter square per kilogram square, or 6.67 into 10 to the power minus 8 Dine centimeter square per gram square. Okay, so we are going to derive a common formula that connects acceleration due to gravity and gravitational constant for any planet. Let's take the example of an Earth for the derivation. Suppose Earth is a perfect sphere of radius r and mass m. Consider a body of mass m that is held at a distance r from center of Earth. Fine. So you see this a diagram to understand what I am saying. Mass of Earth or mass of planet is m, radius of Earth is r, and there is an object of mass m on that planet or Earth, and that object is at r distance from center of the planet, center of Earth. Then between the object of mass m and mass of Earth, between these two masses which are separated by r distance, the force of gravity is calculated using g m1 m2 by r square, that is by universal law of gravitation. So that is one way of using force formula, but there is one more force formula by Newton's second law. Newton's second law is F is equal to ma, but this is acceleration in vertical direction. Acceleration in vertical direction, a is written as a g, so F is equal to mg. So equation 1 is F is equal to g mass of Earth, this mass of the object, by r square. Equation 2 is F is equal to mg. So equation 1 and 2, left hand side is F, so right hand side should be equal. Right hand sides are mg, and for equation 1, right hand side is g mass of the planet, mass of that object, by radius of that planet square. These two cancel, we get a formula that connects acceleration due to gravity of that planet and on that planet and universal gravitational constant. So g is equal to gm by r square. So this is the formula by which we can calculate that every object on or any object on a planet is accelerated towards or decelerated from that planet with what acceleration or deceleration. That calculation, for that we want universal gravitational constant, mass of that planet, radius of that planet. This much information is enough to tell how much acceleration is produced in any freely falling body on that particular planet. You remember this formula, g is equal to gm by r square. Also observe that acceleration produced, g of Earth is 9.8 meter per second square. That means any object that is dropped on Earth will be accelerated towards Earth at a speed of 9.8 meter per second in every second. Means 9.8 meter per second square will be the rate of change in velocity on the planet Earth. This depends upon what factors? This depends upon all constants only, which is a universal constant, mass of planet, radius of planet. So that means that this g does not depend upon mass of the falling body. This formula is independent of mass of falling body. That means whenever an object is dropped on that planet, the falling object's mass has got nothing to do with the acceleration produced in it. That is the reason due to which a heavy boulder or big boulder and a feather or a paper, if they are dropped from the same height at the same time, if it is a vacuum, both of them land on the surface of the planet at the same time. Reason? Both the bodies are accelerated with the same acceleration due to gravity. So here speed is the same, time of start is same, so time of finish is also same. So what is the significance of G? Like why are we learning about G? Significance of G. Acceleration due to gravity is independent of mass of falling body. And this is that question that is given many times as a reasoning question. The question is, a feather and a boulder, big boulder, dropped from the same height at the same time. Which one, according to you, reaches the earth's surface first? Reason out. So I'll tell you a reason here. Just see. See, this is a starting point and this is the finishing point. And here there are two vehicles. So this is one vehicle and this is another vehicle. These two vehicles are of same model. They are new. They run well. And on the first vehicle, a huge elephant is sitting. And on the second vehicle, a small ant is sitting. Now both of them has to reach the finishing point traveling in a straight line, means distance between these two is the same. Distance that they are traveling is same. They start from the same time and they travel the same distance. And we will tell the elephant and the ant to travel at a speed of, the speed limit is 40 kilometers per hour. What do you think? Which is going to reach the finishing point first? Since both of them started at the same time and they have the same speed, they are traveling the same distance, so both of them will reach the finishing point together. So here the mass of the object on the vehicles has got no role to play. Their speed matters, the time of start matters, and place of start matters. Similarly, in vertical direction also, the mass of falling bodies has got nothing to do with the time or when they are going to reach the surface of earth. What matters is the acceleration or speed in which or with which those objects are falling. And acceleration or speed with which the falling bodies are falling has got nothing to do with the masses of object. It depends upon a universal constant, mass and radius of that planet. So which according to us will reach the earth's surface first? According to this formula, acceleration produced in both the bodies does not depend upon mass of the falling body. So the big boulder and the feather in vacuum will reach the earth's surface together. But if it is not vacuum, the boulder will appear to have reached the surface first, and the feather, due to air resistance, it travels a long distance and ultimately reaches the earth. Then distance traveled by both of the objects is different, so they appear to have reached one faster and one later. So that. Second, acceleration due to gravity is inversely proportional to the radius of the planet. See, acceleration due to gravity and radius of the planet are in inverse relation. So using this, we can answer one more reasoning question. Why do we weigh more at poles of earth and less at equator? So using this, just see, earth is kind of oval with more radius at equator, and earth's radius is less at poles. So here radius of poles is less, radius at equator is more. So at equator, radius is more. So at a point on equator, since radius is more, g is less. So at equator, acceleration produced in a body is less. And since we know that weight is calculated using the formula mg, so at equator, g is less. So weight of the body at equator is going to be less. Why? Because mass is constant. So an object comparatively weighs less at equator. What about poles? At poles, radius of earth is less. Radius is less, and since these two are in inverse relation, if this is less, this is going to be more. So at poles, g is more. Acceleration produced in an object at poles of earth is more. And since weight is equal to mg, at poles g is more, so weight of a body is more. That means we will weigh more at the poles and comparatively we will weigh less at equator. So variation of acceleration due to gravity at g. So effect of shape of earth on acceleration produced in every freely falling body. Effect of shape. Shape means the same. Equator radius is more, poles radius is less. At poles, g is inversely proportional to square of the distance between the surface and center r. So at poles, radius of pole is less, radius at poles is less, so g is more, w is equal to mg. Since g is more, weight of a body at poles is more. At equator, radius of earth at equator is more, so g at a point on the surface of equator is less, w is equal to mg, g is less, so weight of a body at poles is less. So now we saw how g varies with the shape of earth. Now let's see how g varies with altitude. So here g naught will be the representation for acceleration due to gravity on the surface of earth, and we know acceleration due to gravity on the surface of earth is approximately 9.8 meter per second square. G subscript h, we will take this notation for acceleration due to gravity at a height h from surface of earth. Now at some height from surface of earth, so this is earth, this is a radius of earth, and from surface some height h. At this point g subscript h. So what or how to find acceleration due to gravity at this point, which is at h meters or kilometers away from surface of earth. So g at a height h is calculated as g naught, means 9.8 meter per second square, divided by 1 plus h by r whole square. But this formula is only valid if height from surface of earth is greater than radius of earth. Radius of earth is 6400 kilometers. So if height from surface of earth is more than 6400 kilometers, then we can use this formula to calculate what happens to g. And why we should know g value at a certain height? Because then we will know that object feels weightless or heavy weight at that height. So if h is greater than this formula, but what if that point above the surface of earth, that height is less than radius, means if this h is less than 6400 kilometers, then this formula is not valid to calculate g at that height. So then we will calculate g at that height as g naught times, g naught is 9.8, times 1 minus twice h by r. R is 6400 kilometers. Then g at the depth. So this is earth. So here some tunnel is made, and this is the center. So this is the radius of earth. And then through this tunnel, up to a depth of d, somebody dives or mines, M-I-N-E-S. So at this location, g naught, which is 9.8 meter per second square. But at this location, what happens to g at a depth? Like if we know this, we will know weight at that depth by just multiplying mass to that. So if we know how to calculate g at a certain depth, we will know that what happens to our weight at the center of the earth if we are able to tunnel and reach there. So g at the certain depth is calculated using the formula g naught times 1 minus a depth by r. And when the depth becomes equal to r, means when we mine up to the center, when these two become equal, they cancel. 1 minus 1, 0. 0 times this is 0. So g at the center of earth is 0. In that case, weight of a body at the center of earth is 0. That means a person completely is weightless at the center of earth. Now we have come to a very important proof of this chapter. Prove that weight of a body on moon is a 1/6 its a weight on earth. What does this mean? Its meaning is if an object weighs 36 newtons on earth, it will weigh it's a 1/6, means 6 newtons on moon. That is what we have to prove. So we have to prove that weight of an object on moon is 1/6 weight of the same object on earth. W subscript moon is not weight of moon. An object can't have its own weight. An object can have weight on some other object because weight is defined as the force with which an object is pulled towards center of the planet. So W subscript moon is weight of an object on moon, and W subscript earth is weight of the same object on earth. We have to prove this. For proving this, we should know certain things, that mass of earth is approximately 100 times mass of moon. That is true also. 6 into 10 to the power 24 kilograms is mass of earth. 7.4 into 10 to the power 22 kilograms is mass of moon. So 10 to the power 22 and 10 to the power 24. So 100 times mass of moon is mass of earth. Also, we should know that radius of earth is 4 times radius of moon. This much data is wanted. Then we know that weight is defined as force with which a body is pulled towards center of the planet. So weight and force of gravity are same. So weight of this object whose mass is m on moon is calculated using the formula F is equal to m1 m2 by r square. m1 is mass of moon, m2 is mass of that object, so m here, r is radius of moon. Similarly, weight of this object on earth is calculated using this formula, g, mass of earth into mass of that object by radius of earth square. So divide this. So when we divide left hand sides, divide right hand sides. Left hand side is weight of the object on moon divided by weight of the object on earth. So first we'll write the ratio of weight of the object on moon times weight of the object. Second equation's reciprocal. And then what cancels? G cancels and mass of that object cancels. And then we get a ratio of mass of the planet and radius of the planet. Mass of moon by mass of earth in form of ratio. Radius of earth by radius of moon over all square. And here we will substitute that value, that mass of earth is 100 times mass of moon and radius of earth is 4 times radius of earth. So these two cancel, these two cancel. So here we get 1 by 100 and here we will get 4 square by 1 means 16 by 1. So 16 by 1 into 1 by 100 is 16 by 100. 16 into 6.25 is 100, clear number. And 6.25 can be approximately taken as 6. So this ratio is 1 upon 6. So weight of a body on moon divided by weight of a body on earth is 1/6. And when we cross multiply, we will get that weight of a body on moon is 1/6 weight of a body on earth. Its meaning is, if an object weighs 36 newtons on earth, then on moon it will weigh its 1/6, means 6 Newton on moon. We have learnt that acceleration due to gravity is equal to universal gravitational constant times mass of the planet divided by the square of the radius of the planet. So this is the formula by which we can connect acceleration produced by force of gravity of a place or planet to the universal gravitational constant. And this formula indicates that acceleration produced in every freely falling body is independent of mass of the falling body. Its meaning is, a heavyweight object or a lightweight object, if they are dropped from the same place at the same time, both the objects are going to reach the surface of the planet together. Because in this formula you don't see mass of the falling object. This is mass of the planet. Now using this formula, we can calculate the acceleration produced in every freely falling body on a particular planet. So here we will use this formula to calculate acceleration due to gravity of earth as well as moon. That means any object that is dropped or thrown on earth or moon, with what speed they approach the surface or with what speed they decelerate from the surface. So we will calculate G of earth. We are using the formula G is equal to Gm by r square. So capital letter G is universal gravitational constant, which is 6.67 into 10 to the power minus 11 Newton meter square per kilogram square. Mass of earth is 6 into 10 to the power 24 kilogram, a good number to remember. Divided by radius of earth. Radius of earth, you can remember it as 6400 kilometers, but whenever we use it for calculation, kilometers has to be converted to meters. 1 kilometer is 1000 meters. So 6400 kilometers will appear as in standard form 6.4 into 10 to the power 6. So since it is r square, here square. How to solve this kind of big numbers? So the best way of solving is put all the numbers together and have the collection of 10 to the powers. Like, what are the numbers? Numbers are 667. So don't involve the decimals. So 667, this one, into 6, divided by 64 into 64, because square is there. Now let's have the collection of 10 to the powers. 10 to the power minus 2 due to this decimal, then 10 to the power minus 11, then 10 to the power 24. This decimal contributes a 10 to the numerator, but since square is there, so this decimal contributes 100 to the numerator. So after 24, this 2 is due to this. Then 10 to the power 6 to the power 2 means 10 to the power 12 in the denominator is actually 10 to the power minus 12 in the numerator. So this is a collection of 10 to the powers. Here we add all the positives. 24 plus 2 is 26. And then from the sum of positive, we subtract the sum of negatives. So minus 2, minus 11, minus 12 is minus of or negative of 25. When we multiply these two, it is 4002. When we multiply 64 into 64, 4096. 40 upon 40 is 1. But you see, the 4-digit number, denominator is big. In that case, the overall fraction value is a bit less than 1. A bit less than 1 means we can take it as 9.99. Like it should be 1 actually. If it was 4000 by 4000, it should be 1. But denominator is a bit greater, so it should be a bit less than 1. Means 0.99 or 98 or 97. So I have chosen 98. And this is 10 to the power 1. 0.98 into 10 is 9.8. 9.8 meter per second square is the acceleration of a free fall of Earth, of an object on Earth. That means every object that is dropped on Earth will travel towards Earth with a speed of 9.8 meter per second in every second, because force of gravity is constant. So every freely falling body will be falling towards Earth with a speed of 9.8 meter per second in every second. That was g of Earth, which during calculation sometimes is taken as a 10 meter per second. So downward is acceleration 10 meter per second square. If object is thrown up, that decelerates. So minus 10 or minus 9.8 meter per second square. Now we will calculate g of moon. Same formula here. G of moon is 6.67 into 10 to the power minus 11. Mass of moon is 7.4 into 10 to the power 22. Radius of moon is 1740 kilometers. When we convert to meters, it appears as 1.74 into 10 to the power 6. Since r square, so here square. How to solve? Put all the numbers together, have the assembly of numbers. 667, 74, 174 into 174. So this is the assembly of numbers without any decimal. Now we will collect the 10 to the powers. 10 to the power minus 2 due to this, minus 11 due to this, minus 1 due to this, 10 to the power 22. This contributes because decimal is after 2 digit and there is a square. So this contributes actually 100. But because of this 100 into 100, 4 zeros in the denominator. But that when it is brought to numerator, it becomes plus 4. 10 to the power 6 to the power 2, 10 to the power 12, it is in the denominator. So when we bring it to the numerator, minus 12. These numbers we have to sincerely multiply, and this also we should multiply. When we multiply, we get 49,358 and 30,276. Now how to divide? Here you see numerator is big, denominator is small, but number of digits is same, 5 digit, 5 digit. So just concentrate on this 30 and 49. So 30 into 2 is a 60, but 49 can be considered as a bit close to 50. So 30 into 2 is a 60, but 60 is very close to 50. So it's not 30 into 2, but it is definitely a bit less than 2. So when we divide these two, we will get something not greater than 2 but very close to 2. So 1.6. Really, when we divide this, we get 1.63, but you can go for approximate 1.6. Here 26, 22 plus 4, 26, and all the negatives when we add, we get again 26. 26 minus 26 is 0, 10 to the power 0. Any variable or number to the power 0 is 1. So it is 1.63. Acceleration due to gravity produced in a freely falling object on moon is 1.63 meter per second square. This number is actually 1/6 of 9.8. That means G of moon is actually 1/6 of G of Earth, means 9.8. When we divide by 6, 9.8 by 6 is actually this number. Now coming to the theoretical part of the chapter, what is the difference between small letter g and capital letter G? It's not the English alphabet small letter g, capital letter G. It is what is the difference between the acceleration produced in any object on a particular planet due to force of gravity of that planet and a universal constant. Acceleration due to gravity and universal constant. So there are some typical points that I have jotted down here in form of a tabulation. So G, the first point always is the definition point. So first point is G. It is the acceleration due to gravity, that gravity has a common force. So same forces apply to all of them. So all the objects on a particular planet have the common acceleration of free fall. G is a variable. This varies from planet to planet as well as place to place on the particular planet if the planet is not a perfect sphere. SPHERE, sphere. What is G? It is the universal gravitational constant and it is same throughout the universe. That is why it is called universal gravitational constant. Second point, acceleration due to gravity is measured in terms of meter per second square, SI unit. SI unit of universal gravitational constant is Newton meter square per kilogram square. Acceleration is a vector quantity, so acceleration due to gravity is also a vector quantity. Universal gravitational constant is a number. So numbers are actually magnitude. So it should be a scalar quantity because it has got only magnitude. 6.67 into 10 to the power minus 11 Newton meter square per kilogram square. Acceleration due to gravity of Earth 9.8 meter per second square approximately, of Moon 1.63 meter per second square approximately. So with this itself we understand that G varies from planet to planet, definitely from place to place also. In the previous part of the video we have seen that G varies with respect to shape of Earth, means at equator some value of G, at pole some other value of G. G values with respect to height, with respect to depth, those all. Universal gravitational constant is 6.67 into 10 to the power minus 11 Newton meter square per kilogram square, or in CGS system 6.67 into 10 to the power minus 8 dyne centimeter square per gram square. How to calculate acceleration due to gravity? Using the formula G is equal to gm by r square. G is universal gravitational constant, m is mass of the planet, r is the radius of the planet. Universal gravitational constant can be calculated using the formula Fr square by m1 m2. This is taken from the universal law of gravitation mathematical expression. Moving ahead in gravitation chapter, we come to the topic thrust. Before we come to the topic thrust, we should know that thrust is also a kind of force. Then how many types of forces are there? There are many types of forces, but those many are actually examples of forces like magnetic force, electrostatic force, muscular force. Those are examples of force. So then we have categories of forces, like we can classify them as contact force, non-contact force, or conservative forces, non-conservative forces. Those all are fine. So thrust is into a category of forces where we understand them or identify them based on how this force is applied to an object. Like for example, every opposing force is into a category, and that kind of forces are called frictional force. Every force that acts on a body for an instant of time that brings about vast change in momentum of the body, those category of forces are called impulsive forces. Then thrust is a category of force or those forces which act on a surface in a direction perpendicular to the surface. Means every perpendicular force can be called as a thrust. When did you see thrust? We will see thrust or we apply thrust Whenever we try to punch a paper on the notice board by means of a ball pin, or when a nail is being hammered on a wall, we don't apply force, we apply thrust. Rockets apply thrust to the surface of Earth and they are launched in a perpendicular direction. So thrust is that. What is thrust? Thrust is the force acting normally on a surface. A force that acts normally on the surface is called thrust. Normally means perpendicular. A normal meaning is something that is perpendicular to a surface. So every force that acts in a direction perpendicular to a surface can be called as a thrust. Since thrust is a force, it is a vector quantity. And what are the ways of, or what are the units in which this perpendicular force can be measured? This perpendicular force can be measured in terms of SI unit, in terms of Newton, in terms of gravitational unit as kilogram force. So thrust is a perpendicular force. So when it is applied in linear direction, means horizontal, not linear, horizontal direction, then force is measured in terms of Newton. But if thrust is applied in a direction vertical, with respect to ground of course, then thrust will be measured in terms of gravitational unit of force. Gravitational unit of force is kilogram force or kilogram weight. In that case, what is the relation between a gravitational unit of force and SI unit of force? One gravitational unit of force means kilogram force or kilogram weight is equal to or approximately equal to 9.8 newtons. How this relation is achieved? This relation is achieved when we know the definition of gravitational unit of force, that is 1 kilogram force. What is a 1 kilogram force? 1 kilogram force is the force exerted by Earth or a particular planet on 1 kilogram mass. So force is actually mg. If mass is 1 kilogram and if it is Earth, then g of Earth is 9.8 meter per second square. Then 1 into 9.8 is 9.8 and kilogram meter per second square is Newton. And this is by definition of 1 kilogram force or 1 kilogram weight, which is the gravitational unit of force. So 1 kilogram force means force applied on 1 kilogram mass by Earth is equal to 9.8 newtons. Now coming to pressure. How to define pressure? Pressure is the force acting on unit area of surface, or it is a force acting on unit area of a surface, that is pressure. So pressure is force per unit area, but remember this is a layman's language. When we say pressure is force per unit area, we should be specific in telling that which kind of force defines pressure. The force which acts in a direction perpendicular to any surface, that force is responsible for creating pressure. So pressure is actually thrust per unit area. So pressure is thrust per unit area. Thrust is measured in terms of newtons. Area is measured in terms of square units. So pressure is measured in terms of Newton per meter square. And what is 1 Newton per meter square? 1 Newton per meter square is the SI, Standard International Unit of measuring pressure. So SI unit of pressure is 1 Pascal. Pascal is written as capital letter P with A small letter, and 1 Pascal is 1 Newton meter inverse square, or you can write it as 1 Newton per meter square. That is SI unit of measuring pressure. Now let us define what is a 1 Pascal. So very simple, based on this itself we can define. Whenever 1 Newton of force is applied on a surface of 1 meter square area, then pressure applied is a 1 Pascal. 1 Pascal is defined as the pressure exerted on a surface of area 1 meter square by a thrust of 1 Newton. So pressure is thrust per unit area. Then we should know what are the units in which pressure is measured. SI unit of pressure is Pascal. 1 Pascal in simplified form is 1 Newton per meter square. 1 Pascal in CGS conversion is a 10 dynes per centimeter square. Actually 1 Newton is 10 to the power 5 dynes and 1 meter is 100 centimeter. So here 100 centimeter square means denominator 10 to the power 4 will come. 10 to the power 5 dyne by 10 to the power 4 centimeter square. So when they cancel, we are left with 10. So just remember this one line. SI unit of measuring pressure, any pressure in fact, is 1 Newton per meter square or a 10 dynes per centimeter square. Pressure can be measured in terms of gravitational unit of force also. So gravitational unit of pressure is force, gravitational force per unit area. Gravitational force is kilogram force or kilogram weight. And remember what is 1 kilogram force? 1 kilogram force is the force applied or exerted on 1 kilogram mass of an object on earth, if it is about earth. So 1 kilogram force is 10 or 9.8 newtons. So 1 kilogram force per meter square, 1 kilogram force per meter square is 10 pascals. For meteorological purpose, pressure is measured like meteorological purpose means atmospheric pressure. How do we measure atmospheric pressure? Atmospheric pressure we measure it using a device called barometer, which is generally fixed to the wall, which will have mercury in it and its length some 1 meter. When in the barometer mercury level is 76 centimeter, then we say that that barometer is placed at a normal atmospheric pressure, means at sea level. So pressure is measured using a device called barometer. So for meteorological purpose, pressure is measured in terms of bar. Maybe this is a part of barometer in that way. How much is 1 bar? 1 bar is 10 to the power 5 pascals. Pascal is SI unit. Therefore, unit of pressure in SI unit is Pascal. Gravitational unit of pressure is a kilogram force per meter square, which is at 10 pascals. Then atmospheric pressure. Atmospheric pressure is not told in terms of pascals. Instead, 1 atmospheric pressure is always informed as 76 centimeter of mercury. To calculate atmospheric pressure or any pressure, we use a formula called P, pressure, is equal to H rho G. H is the height of mercury column in the barometer. Rho is a density of mercury. Density of mercury is a 13.6 gram per centimeter cube. Since it is in CGS unit, we should tell what is acceleration due to gravity. G is that in CGS unit, that is 980 centimeter per second square. That means density of mercury is a constant, G of earth is a constant. If we just read in the barometer the height to which the mercury level has risen or fallen, in fact, that H if we plot here, we can calculate pressure. So 1 atmospheric pressure is calculated in that way. 1 atmospheric pressure is H, means 76 centimeter into 13.6 gram per centimeter cube into 980 centimeter per second square. When we multiply all of them, we will get 1 atmospheric pressure as 1.013 bar. And we know that 1 bar is 10 to the power 5 Pascal. So we can write it is 1.013 into 10 to the power 5 Pascal. So 1 atmospheric pressure means air pressure at sea level is 1.013 into 10 to the power 5 Pascal. 1 bar is 10 to the power 5 Pascal. 1 torr. Torr word has come from the word torricelli. Torricelli, that word is found in the simple barometer making where in the thermometer, that liquid that is taken and inverted into a water containing a trough, then the gap left in the upper part of the test tube, that is called torricellian vacuum. So this is that. So 1 torr is the lowest unit in which pressure is measured. So 1 torr is only 1 mm of mercury. Now coming to some examples on pressure that we see in the textbook. Since we know that pressure is thrust per unit area, this indicates that pressure and area are inversely related. That means if area on which a thrust is applied is less, pressure exerted on that surface is more, and vice versa. So what kind of examples we will see in the on the topic pressure? Example is why school bag straps are wider. So school bag straps are wider because if area of the school bag straps is more, then whatever be the number of books we carry in it, they are responsible for exerting pressure on the shoulders. So since area of straps is more, pressure exerted on the shoulders is less. That is why school bag straps are wider. Then we see some examples like why do we go deep inside a cushion when we stand, but we don't go deep inside the cushion when we lie down? Because when we stand on the cushion, our feet area is less. So more pressure is exerted on the cushion and we go deep inside. But when we lie down, we are on a large area. So since area is more, pressure on the cushion is less. So we don't go deep inside the cushion. Similarly, why it is difficult to walk by wearing high heels in sand. So area of heels is less, so pressure is more, so our feet goes into the sand. Whereas it is easy to walk by wearing canvas shoes. Canvas shoes are flat at base, so area is more. So if area is more, pressure is less. So wearing canvas shoes, we don't go deep inside the sand. Now coming to pressure in fluids. Fluid is something that flows. So liquids and gases are together called as fluid. So there's a common word for liquids and gases. So about pressure in fluids. So first we should know what is Pascal's law. Pascal's law is a very important law when we learn about pressure or fluid mechanics, when we learn about it. So what is Pascal's law? It states that a change in pressure at any point inside a fluid which is at rest is transmitted equally and without any change in all directions to every point in the liquid. This is known as Pascal's law. How to understand Pascal's law? Very simple. Fill a balloon full of water and just press it with your hand, with your fist hand. When you do so, you will see that since you have applied pressure on the liquid, whatever pressure is applied on the liquid, that pressure is equally and evenly transmitted in all directions to every corner of the liquid. As a result, you will see that the balloon filled with water just comes between our fingers. So whenever you press a balloon like this, the balloon parts will come between our fingers, just to tell that the place where the pressure is applied, that is compensated through this pressure, which is in pressure is equal to out pressure. So pressure is equally distributed. That's Pascal's law. And now we come to the topic upward thrust or up thrust or buoyant force. So what is the other name of buoyant force? It is called upward thrust or up thrust. What it is? It is the upward force that is exerted by a fluid on an immersed object. So you can guess it. Whenever we try to put any object on a liquid, the liquid tries to push the object. It is because in physics, two objects cannot be at the same place at the same time. So there is already liquid. We can't have another object at the same place. So the liquid tries to push it. But since liquid's density is less, the solid object, if the object is solid, can go inside, but in that process some amount of liquid will be displaced, means overflown. The property of the fluid to exert buoyant force, means upward thrust, on the immersed object is known as buoyancy. So buoyancy is a property that is seen due to upward thrust or buoyant force. And when we see buoyant force or upward force, we will see whenever an object is immersed in a fluid. Now we come to the topic of density. What is density? Density is defined as mass per unit volume of a substance. We show mathematical expression for density as rho. This is RHO. This is how we represent density. Density is a mass per unit volume of that fluid or the substance. A density, every substance has its own density. Like lead is the densest substance and gold, silver, platinum are rarer, means not denser among solids, like that. So in one unit volume of that particular substance, how many molecules of that substance is there, that defines a density. Like aluminum density is so less, silver density, gold density is so less that we can hold a sheet of silver or gold and just we can tear it. So less denser. But those substances whose density is more, it is difficult to tear. Density is the mass per unit volume. SI unit of density is kilograms per meter cube. CGS unit is gram per centimeter cube. So all the units we can find from the formula itself. Here something to be known is 1000 kilograms is 1000 kilogram per meter cube is 1 gram per centimeter cube. This calculation we can do. So like 1 gram is 1 by 1000 kilograms and 1 centimeter is 1 by 100 meter. But here cube is there. So when we do that, we put the numbers in terms of kilograms and meters. We will get 1 gram per centimeter cube as 1000 kilograms per meter cube. And what is this number? This is actually density of water in liquid state. So density of water is 1 gram per centimeter cube or 1000 kilogram per meter cube. Density of ice is 0.9. That means when ice cube is placed on water, 90% will be inside water, 10% is outside. Why? Because density of water is 1, density of ice is 0.9. So 0.9% water and ice are same. So that is why they will be together. That 10% they are different. So 10% of the ice cube will be seen floating above water. Density of mercury is 13.6 gram per centimeter cube. Now the last but one topic of the theory part of gravitation chapter, it is about relative density. Relative means what? It is with respect to something. So density of an object with respect to something, and here that something is water. How to define relative density? R dot D, relative density. Relative density is the ratio of density of a substance. The substance can be anything, solid, liquid, gas, it's okay. Relative density is density of a substance with respect to density of water at 4 degrees Celsius. So what about this 4 degrees Celsius? Density of water is taken at 4 degrees Celsius because water has a highest density at 4 degrees Celsius. It's not at 0 degrees Celsius when liquid gets converted to ice form or ice form gets converted to liquid form. It's not that. Water has highest density at 4 degrees Celsius. That is why relative density is calculated as the ratio of density of any substance by density of water at 4 degrees Celsius. So when we want to calculate or find relative density of a substance, we have different formulas. I just jotted down those all. Relative density of solid, we calculate using this. So this can be further considered as density is what? Mass per volume. So if volume of the substances are same, relative density can be calculated as the ratio of masses of the substances. So relative density of a solid can be calculated as the ratio of mass of a substance by mass of equal volume of water but at 4 degrees Celsius. That's important. Similarly, mass into acceleration due to gravity. You multiply g, acceleration due to gravity, to the numerator and denominator, then mass can be written in form of weight. So what is the relative density of a solid in terms of weight of the body? It is the ratio of weight of a solid in air divided by loss of weight of the solid in water. Loss of weight of the solid in water means a solid weighs something in air, but when it is placed in water, water pushes it up. As a result, it feels weightless in water. So whatever is the difference of weight of the solid in air as well as water, that is called its loss of weight. Means in air, if it has weighed 10 Newton and in water it has weighed 8 Newton, then the solid lost 2 Newton of weight in water. So relative density of a solid can be calculated as the ratio of weight of the solid in air, that is 10 Newton, by loss of weight of the solid in water, that is 10 minus 8, means 2 Newton. If not loss of weight of solid in water, it can be weight of water displaced by the solid. So whatever is the loss of weight, that 2 Newton is actually equal to the weight of water displaced when that solid is placed in water. Water gets displaced, flows away, overflows. Relative density of solid can also be calculated using the formula ratio of apparent loss of weight of a body in liquid to apparent loss of weight of the body in water. Okay, this is a relative density of a liquid, because when it is a liquid, we cannot drop it in water to check its density or loss of weight. So how to calculate relative density of a liquid? Then what we do is we take a solid, and that solid weighs how much in water, how much in liquid, and from there we find what is its loss of weight in the liquid when it is immersed in liquid to what is the loss of weight of that solid in water. That ratio will give us relative density of the liquid under consideration. Now coming to Archimedes' principle. This principle was stated by Archimedes, a philosopher and a scientist, who accidentally found a method by which any metals or any substance purity can be checked. So a point of time when Archimedes gets into the bathtub, then he identifies that some amount of water is displaced, and keeping this in mind, he goes to the court and tells that he can find a method by which purity of the amount of gold present in the crown can be found. So that's a big story. That's a very interesting story on Archimedes. Now what Archimedes' principle states? Archimedes' principle states that whenever a body, means an object, is partially or completely immersed in a fluid which is at rest. So momentarily you think that the fluid is water or a liquid. So whenever a body or an object is partially or completely immersed in a liquid which is at rest, then that object experiences an upward thrust. That you can experience also, like you can hold a mug full of water, and that mug full of water, when you are holding it outside in the air, it appears to be heavy. But the same mug full of water, when you lower it or immerse it in a bucket of water and then you try to hold it, the mug full of water appears to be light. Why? Because the mug full of water inside the bucket of water loses weight. What is the meaning of losing weight? Meaning of losing weight is when it is in air, it was completely pulled by the center of earth, means by force of gravity. But when it is in water, it is then also pulled by force of gravity, but the water in which the mug full of water is immersed, that mug experiences an upward thrust. Like when we try to put any object in a liquid, so liquid exerts an upward force, tries to push the object upward. That is the buoyant force. Because in physics or laws of physics, any two objects cannot occupy the same place at the same time. So if the liquid is there, it would like to be there. It won't allow any other object to come in. In the process, it pushes that immersed object, and that pushing is called buoyancy or upward force. So Archimedes' principle states that when a body is partially or completely immersed in a liquid at rest, that object or body experiences an upward thrust. And here by Archimedes' principle, the method of knowing how much upward thrust that immersed object experiences can be found. So Archimedes says that upward thrust that the object experiences when it is placed in or immersed in a liquid, that upward thrust is equal to the weight of the fluid displaced by the object. That means when we put an object in water, some amount of water overflows. If the object is placed in a brim full of bucket, like that. So Archimedes' principle states that whenever an object is partially or completely immersed in a liquid which is at rest, that object experiences an upward thrust. That amount of upward thrust is equal to the weight of the fluid or liquid displaced or overflowed, weight of the overflowed liquid displaced by the object. Also, by Archimedes' principle, the amount of upward thrust experienced by that immersed object, which is equal to weight of liquid displaced by that object, is also equal to the loss of weight of that immersed object in that liquid. So that is the definition of Archimedes' principle. So due to Archimedes' principle, certain things happen. See, due to that upward thrust acting on the body apparently loses weight, loses a part of its weight, and apparent loss of weight is equal to the upward thrust. So Archimedes tells that whenever an object is immersed fully or partially in a fluid, that object experiences an upward thrust, and there are two techniques of finding how much upward thrust that immersed object experienced. First technique is you have to find the weight of the liquid displaced. Whatever is the weight of liquid displaced is equal to the amount of upward thrust that object experienced. Second is when the object was immersed in the liquid, the object underwent some loss of weight. Means in air it weighed 10 Newton, but when that same object was lowered in water, it weighed 8 Newton. So loss of weight was 2 Newton. So 2 Newton amount of upward thrust or bind force was experienced by the immersed object. Now, by Archimedes' principle, the concluding statement, for a body either partially or completely immersed in a fluid, there is an upward thrust. How to calculate the upward thrust? Upward thrust is equal to the weight of the fluid displaced, not volume, weight. So we can find weight of a fluid displaced also. That, like, we can have an empty container, we can find its weight using a weighing machine, and later on in that container we can collect the overflowed water, and now with the water we can find its weight. So container plus water minus weight of the container, when we can get weight of the fluid displaced. So upward thrust is equal to weight of fluid displaced, which is equal to the apparent loss of weight of that object in that liquid. So this is something that is told by Archimedes. And since Archimedes' principle talks about law of flotation, that whether an object is going to sink or float, so that point I'll discuss here. How to know that an object is going to sink in a fluid or float on a fluid? So for example, I'll tell about water. Water's density is 1. Any object whose density is greater than 1 will sink in water. Any object whose density is less than 1 is going to float on water. So based on this, what I said, we can figure out that whether an object is going to sink or float in any fluid. For sinking, the condition is the object's density should be greater than density of the liquid in which it is dropped. If density of the object is less than density of that liquid, then the object floats. Law of flotation states that weight of floating body in a fluid is equal to weight of fluid displaced by the body when that floating body is immersed in water. So we have a topic called mass and weight. So let us first learn it in form of difference between mass and weight. They look alike but they are different. What is the mass? Mass is actually denoted by the letter small letter m or capital letter M. Weight is denoted by the letter W or F. So mass is what? Mass is the quantity of matter possessed by a body. The quantity of matter possessed by the body. That means how much amount of content is there in a body is called its mass. Whereas weight. Weight is the force with which an object is pulled towards center of the planet. So weight is a force. Mass is the quantity of matter possessed by a body. How to measure mass? Mass is measured by a device called beam balance or simple balance. The one that we see in gold shops. Weight is measured by a device called spring balance. Spring balance is a kind of device which will have a spring, and to the one end of the spring we put there will be a pan, and on the pan when we put something and hold the spring, that spring extends due to the force with which that object in the pan is pulled due to force of gravity, and we will read what is the weight in terms of newtons. Mass is measured in terms of kilograms, which is SI unit, or grams. Weight of a body is the force with which an object is pulled towards center of the planet, so it is measured in terms of newtons. Mass is a constant. Mass of an object is always constant. Mass can't vary, so it is a scalar quantity. Weight is that varies from place to place, planet to planet. Why? Because weight is calculated using the formula m into g, mass into acceleration due to gravity of that place or planet. And since g is a variable thing, though mass is constant, weight of a body is also variable. So it is variable as well as it is a vector quantity, because weight is the force and force is vector, so weight is also a vector quantity. So mass is a constant for every object. Every object has got their own mass, but weight varies from place to place, planet to planet.